Hey, David here from Agile Tech Support. Today I'm talking about the application software and the infrastructure software that go into creating backups and then being able to recover a machine state by restoring those backups. When we're talking about backing up entire workstations or home computers, it's not as simple as just copying files from one storage disk to another. Creating a system backup is a similar concept but a different process when compared to file synchronization and file backup. There's a wide range of backup and recovery applications on the market that do all of the above, and there are several storage types that have been used over the years. Businesses will typically back up emails, documents, accounting data, stock databases, customer databases, employee databases, multimedia files. I'm specifically going to talk about the technology behind operating system backup and recovery because that's what disaster recovery is all about. But the same technology can be applied to any data type. I'll refer to the operating system as the OS throughout this presentation, by which I mean either a Windows, Macintosh or Linux deployment. So the objectives for backing up an OS are all about disaster recovery, whether by hardware failure, malicious software, or just plain user error. The aim is to build a reliable platform that has zero data loss in the case of any of the above happening. Now, this is not always possible. You generally stand to lose a small amount of work, but the cost of losing that work is considered a fair trade-off compared to the cost of building an absolutely bulletproof platform. Backup is a different process to archiving. Archiving relates to application data files that are moved from so-called hot storage to cold storage. An example would be your email application. It may archive messages older than 6 months on a monthly basis. These emails are simply moved from the main online message database to a separate database, which would usually be online but may be hosted on network storage where the main database is on local storage. This prevents the file size of the local database from growing too large without needing to delete old emails. A backup policy for email data would actually duplicate both the local and the remote database. Recovery points are defined each time a new backup operation is run, and most small and medium business will run these on a daily basis after the finish of trading, so that normal operations are not impacted. The net result should be that we're able to conduct what's called a bare metal recovery for any operating system. This means that we can bring in a brand new machine, even a totally different hardware platform, and recover the OS onto that machine and start working where we left off prior to the problems. Another aim in disaster recovery is to reduce downtime. This is the time it will take to recover the OS and get the workstation up and running again so that business operations can continue. Modern backup and recovery tools are very good at reducing downtime to an absolute minimum. It's usually sourcing replacement hardware that causes the most downtime, so many disaster recovery plans will include having redundant hardware on site. Data security is another factor to consider. The backups should be stored in a secure location, and this is referred to as data at rest security, and the backup operation should occur over a secure network. This is referred to as data in transit security. Larger organizations will often implement a data retention policy that dictates how long specific records must be kept. For an OS, there's usually no point in keeping more than 1 or 2 versions archived because the retention policies usually don't apply to the OS. Whether or not this is applicable to your business will all depend on how you deploy your workstations and the OS. If you have a highly customized OS with multiple user profiles, access control lists, network connections, local documents, multiple native applications, or anything else that takes considerable time to set up, you will want to invest in a disaster recovery solution for your OS. If, on the other hand, you literally only use your workstation for web browsing and email access, then you're probably running a fairly generic OS configuration with very little customization, and hence it's just as easy to install a new copy of the OS. In which case, you should only back up important files and don't worry about a disaster recovery plan for the OS. At the end of the day, it's all about business continuity. A system administrator should configure backup software based on several factors. The backup window, which is the time frame within which the OS is offline or idle and hence can be backed up in a single consistent operation. For host machines that only operate across a single time zone, this is fairly straightforward. But for internet-facing servers and other hosts that operate across multiple time zones, it requires careful planning. If the host is literally active 24/7, then the administrator needs to consider the impact on performance of running an online OS backup and take steps to mitigate this impact. The design of the backup system should include consideration of hardware, software, and labour expenses. For those businesses that don't use what I would call mission critical data and with access to high-speed networks, the cloud computing model is becoming more attractive. For any other business, I would argue that private on-premise infrastructure, or at least a hybrid infrastructure, is still the way to go and can still be done in a cost-effective way. There needs to be a solid network in place between the host machine and the backup data store. There should also be a backup validation process in place to log any errors that occur during the backup and to generate reports for the administrator on a regular basis. Small and medium business will often outsource this validation work to a specialist. Physical storage infrastructure is used to make computer memory persistent between power cycles, whereas other physical memory hardware is volatile, meaning that the memory only works whilst the host is powered on. Persistent storage can be either local to the host machine or accessible via a network connection. Typically, we would use a network storage for backup purposes. Logically, the host machine will see a storage pool, which may be made up of multiple physical devices across multiple network locations. From that pool, the system administrator will have set up logical partitions that reserve certain areas of that pool for certain tasks. Each partition uses its own logical file system to manage data, and each OS has its own rules on what file system it can interact with. Within an online OS, logical volumes are then mounted from one or more partitions. It's important to note that volumes are a runtime view of the storage pool. Partitions are defined in software, but they are defined using a universal storage protocol. Any OS should see the same partitions, whereas a different OS may mount these partitions to different volumes. This then gives the user and the backup engine access to the file system on that volume. An OS is a dynamic, self-managed piece of software. It always starts in an offline state, which means it exists on a persistent storage device, but it's not active and it has no control over the host machine. The boot process is about loading the necessary OS modules into a volatile memory space and configuring those modules based on the specific hardware that is connected to the host. Control of the host is then handed over to the OS and it becomes online. Performing a shutdown or a reboot is effectively the reverse process. The main difference with a reboot is that the hardware stays powered on. There's a few different states that handle sleep, suspend or standby. Other than the fact that the processor stops running and some peripheral devices lose their connection to the host, these sleep states have very little impact on the OS. Hibernate actually copies the entire contents of volatile memory into persistent storage, usually within a single file, then shuts down power to most of the machine. And then recovering from Hibernate is the reverse of that process. For disaster recovery purposes, we're interested in capturing the offline state of the OS, even when a machine is currently in the online state. So a backup engine effectively needs to be able to carry out these shutdown procedures without actually offlining the OS. One of the features of modern workstations is that they run a secure boot sequence. This is a feature that Microsoft introduced several years ago and hardware vendors had no choice but to conform to. I can explain this by going back to the logical partition model, this time for a typical Windows 10 consumer device. So OEMs, or original equipment manufacturers like Dell, Lenovo, HP, will typically create 6 logical partitions on a Windows 10 consumer device. A Windows recovery environment partition, which is a skeleton version of the Windows OS, plus some basic repair tools. This is what your machine boots when the main OS becomes corrupted. A boot partition, this contains the boot load logic that the machine follows before handing control over to the OS. So this is effectively where the boot process is launched from. A very small partition with no file system called the Microsoft Reserved partition. This is purely there to make partition management easier for the OS. The OS partition itself, which usually also includes all the hardware drivers and the application software. An empty partition for storing user data. And then sometimes you will also get a recovery image partition. This is usually what's known as a reference image that was created by the OEM, and it's used to do a factory reset on the operating system. So from Windows 8 onwards, this was known as a push button reset feature. From these partitions, 5 volumes are created, of which a standard user can only see 2. Admin users can see all 5, but the graphical interface will only ever show 2. Secure boot means that the logic within this purple boot partition must be digitally signed, or the OS simply will not boot. This is to stop malicious actors overriding the boot partition. What this means for a backup scenario is that a full system backup must contain data from the boot partition and from the OS partition, plus any files within the data partition that an administrator wants to back up. Volume encryption is also an issue for backup engines. So volume encryption requires that the host machine has a crypto processor implemented in hardware. Here the entire OS volume and probably the data volume are encrypted using a key stored within the boot partition. The boot process uses this key to decrypt the OS modules that it loads into main memory. Once the OS goes online, it then accesses the same key to read and write data within those volumes. These encrypted volumes are just gibberish without the encryption key. And this is where the backup engine needs to either decrypt the volume as it's being backed up or back up the encryption key as well. Cloning and imaging are 2 methods for copying entire disk partitions. So cloning creates an exact bit-for-bit replica of the original partition. So effectively a mirrored copy. Imaging only recreates the information, that is, the necessary data and file system metadata. Free space and physical layout are ignored, so you end up with a completely unfragmented, organised version of the original partition. The advantage of a clone is that as long as that clone contains the necessary boot partition, you can swap the clone disk in place of the damaged disk and you're done. The reason we don't use clones much anymore is that they literally need to be recreated as a full clone each time you want to run a backup. They are not flexible to incremental backups, etc. They require extra time, space and resources compared to imaging technology. So the main job of the backup and recovery engine is to create full partition images, usually triggered by a scheduler that runs as a background service and requires administrator privileges. It should be flexible in the way it can be configured. It should interpret the file system within the partition so that the individual files or folders can be backed up and restored. It should also contain a shell or user interface, usually both a graphical interface and a command line interface for remote admin. It should be able to purge or delete old data when necessary to make space for new backups. The destination for the backup images is known as the data repository. Similar in function to a database model, but more suited to large, infrequent transfers, where a database is better suited to small, frequent transfers. So where a volume is a logical interpretation of the partition by the file system, a repository model is simply blocks of data, no interpretation, usually hosted by a server OS within a single file. The simplest repository model is unstructured. This is typical of manual backups to external drives. But it's not a reliable repository and it's not what backup infrastructure is all about. A full system image is usually done on the very first backup and then on a weekly or monthly basis. So going back to our partition view, this would convert an entire volume into an image, which then becomes a large file in the repository. Incremental backups are the most common model. This type of backup would usually happen on a daily or hourly basis. Incremental backups only store new or modified data since the last backup, eliminating the need to store duplicate data. This is a critical feature in modern backup engines. It makes the regular backup cycle much more cost effective by dramatically reducing the backup time and the hardware requirements. Recovering an image is then a matter of taking the most recent full backup and applying all of the subsequent incremental backups. A differential backup is similar to the incremental model, except that it stores new or modified data since the last full backup. This typically means backing up more data, but it has the advantage of only requiring a single backup in addition to the last full backup in order to recover the entire image. A reverse delta model is a similar concept to the incremental model, but instead of storing the modified data as a new file, it will apply those changes to the original full image backup and then create a new file containing the process needed to reverse those changes. So you end up with a single full image which has been amended to match the latest version of the volume, plus several previous incrementals which show the changes made to that image. And from this you can actually rebuild previous versions of the image. So this is the model used by Time Machine, which is the backup application that Apple bundles with the Macintosh OS. I suspect iTunes probably uses it to back up iPhones as well. In terms of recovery, it's a superior model because it cuts down on the recovery time and hence the downtime that business will face after a disaster. The most comprehensive zero risk model is the real-time or live backup model. This is where any additions or changes are immediately logged and sent to the repository. No scheduling, just continuous incremental backups. This is a bit extreme for most business operations, and it can consume very significant network resources. Most backup applications will at least offer full, differential and incremental. A good overall policy is to do a full backup every weekend, a differential backup every night, and an incremental backup every hour. Designing and managing the backup repository is a matter of balancing accessibility, security and costs. Online repositories offer a great accessibility and a low cost, but can be a security risk if malicious software spreads through the network. So storage servers range in price depending on requirements, but they do allow for a fully automated backup schedule. Nearline repositories involve hardware that is physically connected but not always logically connected to the host machine. So public cloud storage would be a good example, e.g. Google Drive, Microsoft OneDrive and Dropbox. An offline repository also provides good accessibility and good security for a reasonable price. An example would be implementing network storage via a programmable switch. A layer 2 switch can logically connect the network cable to run the backup and then logically disconnect that network cable after the backup is complete. It could even be set up on a timer, so there's no manual action required. The most secure repository is an off-site, offline backup, but it comes at the cost of low accessibility, expensive recording hardware and regular admin work. An example would be a cassette tape backup system. The backup would run overnight and the administrator would need to replace the tape each day and take the most recent backup off-site, whether that's home or to a secure storage location, depends on the nature of the data. The idea being that multiple tapes are in use at any time and there's always an off-site tape with the most recent backup. This has been the approach used by big business up until secure cloud backup became a somewhat viable alternative for some end users recently. Regardless of the backup model and the way it's managed, the process of creating the backup involves manipulating the data to some extent. Compression may be applied to the image to reduce storage requirements. The image may be duplicated onto secondary storage devices for additional protection. Old images will either be deleted or archived into cold storage. As a part of the compression effort, deduplication may take place on an image. Encryption can be used for additional security. This includes in-transit encryption and at-rest encryption. Multiplexing is the ability to run simultaneous backups across multiple hosts and push their combined images to the same repository. This means that multiple backup engine instances need to work in cooperation to transmit image data along the same communications channel and then demultiplex those images at the repository. Refactoring is the process of consolidating or reorganizing the physical layout of backup images. So let's go back to our repository model. If each of these backups were stored on separate physical devices, and we needed to do a recovery here, then we would need 5 separate devices to fully recover the image. Refactoring those backups would reorganize that data so that only one device was required. And this basically is what the reverse Delta model does as it runs each backup. Staging is only necessary if the repository storage writes data at a slower rate than the backup engine can create and transmit an image. For example, if our image is being read from a solid-state disk, which has a read speed of 500 megabytes per second, but our local network is rated at 1 gigabit per second, or around 125 megabytes per second, then we're going to be reading the image faster than we can write it to the network. And this is where a staging area on the local host is used to buffer the image. With the rise in popularity of virtual machines for endpoint management, the backup and recovery process is becoming more centralized. The thin client with no persistent storage is taking over as the dominant workstation of choice for business. Server infrastructure running commercial grade hypervisors can run dozens of VMs in parallel, and the VM manager serves these guest VM instances out to thin clients via a network connection. This means the offline state for each OS is contained within a single host, the VM server. All that needs to be done is a thorough backup of the VM server. VMs also have the ability to create snapshots whilst they're running, and this is effectively the same as running a full image backup of that OS. The net result is that the traditional backup and recovery vendors are now losing market share to the hypervisor vendors. But virtualization is still really only cost effective for big business. So in conclusion, backup and recovery is all about business continuity. Each solution will have different configurations, but each will contain a backup engine and a repository, which is a combination of hardware, software, and labour. Your backup solution is your last line of defence against data loss. So it should be something that your IT manager has well engineered. And that's it for today. Tune in next time.